Okay, the next problem we're about to see involves drawing a picture using headings and bearings. And this is stuff you've not seen before probably. So let me just real quick talk you through this. So let's start with heading. Sometimes the picture is drawn for you like it is on example 4. Most of the time it isn't. So being able to draw a picture based on a description of headings and bearings is important for the sake of these problems. So if I'm considering heading and bearing, did I say I was going to do bearing first? Or heading second? Oh, good. All right. All right. So if you imagine north as 0 degrees. Okay. Heading is measured counterclockwise from the north, whatever angle they want. So let's say a heading of 72 degrees. So what we would do is we would measure a 72-degree angle off of this. So 10, 20, 30, 40, 50, 60, 72.
Did you say counterclockwise or clockwise?
It's clockwise.
Okay.
Did I say clockwise?
I don't know.
I meant to say clockwise. We can rewind the tape later and find out what I said. But I should have said clockwise. Alright. Oh, dang it. Hold on. Better mark the spot where I was at here, too. Helps to use the protractor correctly. So 72 degrees right there. It won't let me put a mark right on it, but it will. Alright, so if I were to draw a segment, usually heading, they're talking about the direction somebody's moving. When they're drawing stuff, if something's moving somewhere, they're going to give you a heading. If somebody sees something, they're going to give you a bearing. So the ship moved on a heading of 330 degrees, I believe, on the next problem. They spotted a lighthouse at a bearing of whatever. So when they look out, they're at a bearing. When they're moving, they're at a heading. So usually if I draw a heading issue, I'm going to draw an arrowed line representing the direction I'm going. So that's a heading of 72 degrees. As you draw it, label it too. So any angle measures that get in there get drawn. Okay, the other thing we have is bearing. Bearing looks like this, south 20 degrees east, or north 62 degrees west. All right. You're going to get a north or a south, some angle between 0 and 90, and then east or west. All right. So, and how it looks is this. So if I just draw a north-south line like this, north up here, south down here. And let's just say I'm going from this spot right here. So south 20 degrees east means that I'm looking south, and then I turn my gaze 20 degrees to the east of south. All right, so 20-degree angle will be right here. If I'm looking at north 62 degrees west, I'm looking north, and I turn my gaze 62 degrees to the west. So imagine, so if you're like on a ship or something, you look out, let's say that's north, and then I slide to the east, okay? Or I look north and I slide to the west. So the direction you're sliding is the angle that is made with this. If it goes beyond 90, now it's going to be south something degrees east, okay? So that's why it's going to be between 0 and 90. So you look up or down, then you look left or right from there. So whenever they give you a bearing, that's how you draw it. All right? So with that in mind, and this is going to show up in the Law of Cosines, Chapter 2, Headings and Bearings. This is your best description of it. I'm not going to go through this whole thing every time, but anytime I draw something with headings and bearings, that's how it's drawn. All right, so a ship with a heading of 330 degrees, first sighted lighthouse, point B at a bearing of north 65 degrees east. Okay, so the heading of 330 degrees means that if here's the ship right here, its initial spot, here's straight north. 330 degrees means that it goes all the way around there, 330. A lot of times with these heading and bearing pictures, the angle you get is not inside the triangle. It's up to you to get it inside the triangle. All right. So what I can do is determine then that the angle left over in here is what? 30 degrees, right? Now that's not the entire angle made by the triangle there, the entire angle's here. It goes from here all the way around to there, but we'll figure that out in a minute, all right? And it says it spotted the lighthouse point B, so this is the lighthouse. The lighthouse is not moving, it's a stationary point, okay? The ship will be moving, all right? Do have to describe these things. I had students have lighthouses moving fast, so just be careful of that. Lighthouse is stationary. All right, so point B is where the lighthouse is. They spotted it at a bearing of north 65 degrees east. So look up north and then go 65 degrees to the east. That means that that angle right there is 65, which now allows me to determine that the entire angle down there in the corner is going to be 95 degrees. All right? So again, just by descriptions by headings and bearings, we have the ability to get an angle inside that triangle. The ship travels 8.5 miles. It was on a heading of 330, so this is the traveling of the ship. Let's just put a colored line on that. So here's where the ship started, and it traveled at the heading of 330 degrees for 8.5 whole miles. So that's the distance the ship traveled. So the ship's new location's at C, lighthouse is still at B. All right. So then they make another observation here, and they observe that the lighthouse is now at a bearing of south 50 degrees east. Now, be careful of this. You get a lot of lines in this, and it's important you go to the correct line. The bearing was made from point C, and we're looking at the lighthouse point B. So CB is the line we're looking down. So the 50-degree angle goes to right there. Notice that 50-degree angle is not inside the triangle. All right. What we're missing is how big this angle up here in the corner is. And hopefully we can see that these norths are parallel to each other. This ship's path AC is a transversal to those parallel lines. So therefore this 30-degree angle should match this 30-degree angle here. And if that 30-degree angle is there, obviously the angle inside the triangle is going to be 20 degrees. So there's a lot of that, addition, subtraction of angles in order to find a missing angle situation going on. With this in mind, notice that we have this triangle ABC involving the ship's path and the line of sight to the lighthouse from both locations the ship was at. That ABC triangle, we have angle side angle, which is enough information to use the law of sines. The question asks, what was the distance from the ship to the lighthouse at the first sighting? So we're looking for this. We could also find the distance to the ship at the second sighting. Okay, so we have the ability to find either. Okay, me personally, once I've drawn the picture like that, I like to take that out and make, because it gets like, because it got all these angles and stuff in here. So if I just were to draw ABC real quick, and it doesn't have to draw to scale, but I try and get kind of close. So there's ABC, and just get the pertinent information out of this. AB is 8.5 miles. This angle down here in the corner, altogether, 30 and 65 makes 95 degrees. And this angle up here in the corner is 20 degrees. It's just a lot nicer to look at it like this, and we're looking for this little C here. Which I don't like. Oh, I was going to say, I don't like to see me putting the wrong letters there. All right. Why they put C opposite B? It's my fault. All right. And obviously, we need to know the measure of angle B because we're using law of sines, 8.5 over sine of B. 20 and 95 make 115. Subtract that from 180, we get 65 degrees. All right. So, I know 8.5 over the sine of 65 should equal C over the sine of 20. And I get my calculator out, sine of 65 and sine of 20 should be known by my calculator. Again, verifying I'm in degrees, not radians. It makes trigonometry not work very well in the wrong mode there. 0.9063 and 0.3420. So to get C, I'm just going to cross multiply this product divided by that. So 8.5 times 0.3420. Divide that by 0.9063. Just typed in right, it is. We get 3.21 miles. All right. So expect the law of sines to be present in every problem. If you're looking for angle, side angle, 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 side, or side, side angle, in that third scenario, there's a possibility of two sets of answers. Sometimes it could be narrowed down to one set of answers based on the drawing itself. If you can see an obtuse angle in your drawing, then it's going to be the obtuse one. If there's not, it's not. So that happens sometimes when you start getting real problems in the real world. But again, there's times though there two answers are possible. So account for that scenario by giving me two sets of answers. But if a picture's already drawn for you with a, let's say angle B is supposed to be obtuse, go with the one with angle B as an obtuse measure like that. So that'll help you narrow down the set of answers you're looking for in that scenario. And again, just because the law of sines chapter doesn't mean we can't revert back to just basic trigonometry like we did in example 3, where we have a basic right triangle here. A lot of times you get right triangles in these pictures. If you do, you're still allowed to use the SOHCAHTOA stuff, sine opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent to find missing side. So keep that in mind. Keep it basic as much as you can. Law of sines is a little bit more advanced, but it's not that terribly difficult either. So just be expecting that, and that's how they'll work.